All right, well, let's deal with the first issue that we just talked about, and it's the fact that basically the current that goes through the load resistor is directly coming from the op amp. So let's just take our op amp, like so, the inverting, not the non-inverting, this is where we inject the voltage, we call it V in. The inverted here would be tied through a resistor to the ground, and instead of this providing me directly with the current through the load, here's what we're going to do. We're going to run it through a transistor, and then our load will be over here. Let's call this VCC. Alright, this is our load. So it attaches here and here. And this is R. Now since we're using basically a negative feedback, that means V minus, V plus, which is V in is equal to V minus, which is also V in. So V in is over here, and that's what defines, this is V in, what defines this current, I. We still have I equals to V in over R. But now here's the novelty. The current I, by the way, this I here, is the same as the current I here, practically speaking. And there's a tiny difference, but we're going to simply say that I through the load resistor is practically the same as I through R. Reason being simple, I through the load resistor is basically the collector current. This is our collector, and this is our emitter, all right, and this is our base. So these currents are practically equal, and there's a difference, but it's so small that we can simply ignore it. And here's basically the novelty. I is not directly generated by the op amp. I is actually generated by this voltage supply that is applied from here all the way to the ground. So what generates I is not the op amp, but this one in here. But then again, how do we get I? Well, if we have a current coming out of the op amp, and it's typically a fairly small current, by the way. I can get this too. All right. So I have the current coming out of the op amp, which is a fairly small current. And since this is a transistor, what the transistor does is that it's going to simply take I out of the op amp, and it's going to generate a much larger current. All right, let's call it IRL, which is the current through the load. And the relationship is very simple. I through the load is simply the beta of our transistor here times I out. Now this is simply a rewriting of I out, which is the current that is going through the base, IRL, which is the current going through the collector, and we know that these are related through the current gain. So now I can get a fairly large current flowing through my load resistor without that current being directly generated by the op amp. So what this circuit does is that it solves the first problem that we dealt with previously, which is now I through the load is not generated by the op amp. It is generated by a voltage VCC Alright, so what we're going to do now is we're going to deal with the second issue. If you remember, we had two issues with the op-amp used as a current source. The first one being that the current that was flowing through the load was coming from the op-amp, and op-amps cannot generate typically large currents. And we did come up with a fairly good solution. And now we are going to deal with the second issue, which is a floating load. So here's the actual circuit, and then we're going to see how it deals with those issues. So here's my op-amp. All right, this is the non-inverting. This is where we're going to inject a voltage, Vn. The output of the op-amp is going to generate a current that will be used to drive a NPN transistor like we did previously. So every time there's a current here that flows, this is actually flowing into the base of this transistor, there will be a much larger current, IC, in here that flows, and IE is simply the sum of the two. And we all know that IE is almost always practically equal to IC. I mean, there's an IB difference in there. To be 100% correct, we should say that it's IC plus IB. But this current IB is typically so small that we simply ignore it, and we approximate IE as being IC. Anyway, what we're going to have is that we're going to have a resistor in here connected directly to the collector, and the inverting input would be coming from here. There is a power supply in here we're going to call VCC, and my load resistor simply connects the emitter to the ground. So now there will be a fairly large current flowing from here, and that current is not coming from our op-amp. And notice now that our load is now connected to the ground, so it's not floating anymore. So this circuit actually solves both problems. The first one is that the current that flows through here is not directly coming from the op-amp. It is proportional to the current coming from the op-amp, but it's not the current coming from the op-amp. The second thing is that by using this feedback and using this configuration, RL is not floating anymore, it's tied to the ground. Now let's see how this thing works. It's obvious that there's a negative feedback in here. You can easily see the negative feedback, right? So because there's a negative feedback, we can say that V plus is the same as V minus. And knowing that V plus is nothing more than Vn, you can simply say that the inverting input has the same voltage as Vn. So Vn is in here, and Vn is in here. Now let's figure out the current I here that flows through our resistor R. So this resistor, we're going to simply call it R. All right, so you just make up some room in here, create some room. So the difference of voltage across R is VCC minus Vn. And if we divide this by the resistor, we find the current. Now this current is the current going to the collector. Why is it exactly equal to the current going to the collector? Because the current that going to the inverting input is practically zero. So this current is actually the collector current. Now, because this is a NPN transistor, it should have a current gain of beta. So I can say for sure that a collector current is beta times IB. And IB is nothing but the current coming out of the op-amp. So it's beta times I out. So even with small values of currents coming out of the op-amp, we can get fairly large currents flowing from VCC through the transistor. So the transistor here simply takes the current out of the op-amp and amplifies it, and that's what we call the I in here. Now, IC and IB, which is I out, make up IE. So IE is IC plus IB, and IB is nothing but I out of the op-amp, so IC plus I out. And typically IB and this I out are so small that we can ignore them, so we can simply say that IC is practically equal to IE. IE being slightly bigger, but not by much. So now our load is getting the current I here. But here's the beauty of this configuration. This is I, which is the same as IE. Here's the beauty of this configuration. I, which is the current flowing through the load, is equal to VCC minus Vin over R. So I is a function of our power supply, our input voltage, and of R. Notice that I has nothing to do, our current has nothing to do with the voltage. We're going to call it here VRL. So it's not a function of VRL, and it's also not a function of RL itself. So so we can control the current that flows through this load. So we can easily control the current that flows through this load, and the current that flows through this RL in here would look something like this if we were to graph it against VRL. This is I, basically the current through our load, versus the voltage across that load itself. Well, if we keep three parameters constant, if VCC doesn't change, if the V input also remains the same, and if R does not change, then we're going to have a straight line in here. And by definition, when we plot the current through a component versus the voltage across that component, and we find that the current does not change regardless of the value of the voltage, that is the very definition of pretty much the current source. So we have, this is the ultimate current source actually. So this circuit provides a constant current across RL regardless of VRL. We also basically will notice here a couple of interesting things. That IL, which is this current from here to here, the current that is flowing down here, is completely independent of basically the voltage and RL itself. Now it depends upon the voltage supply, it depends upon the voltage at the input, and it depends upon R, and we can control those parameters. And the beauty of this circuit is our load resistor here is not floating anymore. It is connected, as you can see, to the ground. And the current that's flowing to it is not provided by the op-amp, it is provided by the power supply VCC. So this circuit pretty much solves the two problems that we have seen previously. And this would be our final circuit. Now, there are some improvements over this circuit, but this is a circuit that is working fine for our purposes. It provides us with a current that is independent of the voltage VRL across the load. So the current that flows here has nothing to do with this voltage in here. It only depends on the input voltage. It depends on the power supply, and it depends upon R itself, and nothing else. It is also generated by the voltage source VCC that we have here. And furthermore, the second issue that we had previously was that the load resistor RL that we have over here was floating, and here it is not floating anymore since it is connected to the ground. And that basically will conclude our discussion or our lecture about current sources using op-amps.